There is a rich history of using evolutionary concepts and terminology in architecture and design. Designers and architects both adopt evolutionary concepts, language, and vocabulary well before the rise of evolutionary computational creativity tools. Design and architecture share with art that they are about the creation of forms. But unlike the latter, they are characterized by the creation of utilitarian forms. What is great about evolutionary methods for design and architecture is that they can optimize objective parameters, for example, the surface of a building, the inner volume of a bottle, or any other functional requirements of a given design or architecture project. At the same time, they allow explorations of the space of possible aesthetics and styles. A lot of work in evolutionary design and architecture aims to conceive tools for computer-assisted design or architecture, rather than strictly generative systems. These tools for computer-assisted creativity help practitioners to explore the most often gigantic solution space. As we have seen several times already in this course, interactive genetic algorithms are the perfect approach for helping the user navigate the space of possibilities. Interactive genetic algorithms have been applied in graphic design. For example, Matthew Lewis used cartoon face evolution as one of several design domains when developing the interactive evolutionary design platform MetaVolve within a three-dimensional animation environment. This is a screenshot of the tool's user interface in 2000. Interactive evolution changes the creative task from design by constriction to design by exploration. In design by constriction, the user needs to know how to produce the graphic design of a cartoon face. But in design by exploration, the user simply needs to express their preferences. In the domain of font design, Andrea Lund in 2000 used parametric font design to compare interactive evolution and direct manipulation interfaces. He observed that evolution yielded better results for creative exploration, while direct manipulation was easier when given a precisely specified design task with a set of clear objectives. Michael Schmitz created the Flash-based program Genotype in 2004, which allows the user to experiment with breeding different typefaces with an emphasis on drag-and-drop mating. The Alphabet Synthesis Machine was an online project from Golan Levins and colleagues. Users could breed abstract alphabets from a physically based writing model. The project ran from 2001 to 2006, and over 20,000 fonts were created that could be downloaded as TrueType fonts. Open-ended design platforms have also been proposed. The online platform Endless Forms supports the interactive evolution of arbitrary three-dimensional forms. In evolution mode, it displays 15 forms slowly rotating to show the three-dimensional shapes of the forms. The user chooses 2 of these forms to create the next generation. The site can export the creation in many formats, including three-dimensional printing formats with direct links to 3D print-on-demand services. Endless Forms aims to meet the demand from users who might not have the skills to design their own 3D dimensional object, but who, like most, have their own needs, opinions, and preferences. Many people are skilled critics who know what they like and what they don't like when they see it, but are not capable of creating their own design from scratch. Endless Forms allows users to browse or search for existing forms and start developing new variations from one of those existing forms. Here we have examples of forms that look like lamps. Users without any technical knowledge go to design a wide variety of objects, including doorknobs, jewelry, candlesticks, chess pieces, and abstract sculptures. This platform is a good example of the potential of computer-assisted creativity in the real world and how it can change design practices. These online platforms allow radical customization and parametric design to live up to their full potential. These type of interfaces will be key in the shift from mass production to custom manufacturing, fueled by the three-dimensional printing revolution, if things progress the way they are now. Of course, Endless Forms users can also decide to share their creations. The authors found that some of the most liked items have been collaboratively evolved by users taking previously published objects and breeding them further. The site got good press coverage and attracted thousands of users since its launch in 2011. Interactive evolutionary design has also been applied in other domains besides graphic design and three-dimensional modeling. The idea of evolutionary design has been applied to the design of countless consumer products. Examples include the evolution of shape grammars for the generation of camera design by Li and Tang in 2004. A few researchers have also applied genetic approaches to fashion design by using evolutionary processes to combine pre-modeled three-dimensional garment parts. Duncan Ronan and Frank Bauka developed a system for designing shampoo bottles by asking consumers' panels to sort designs into like and don't like piles so that the final product design emerged from the choice of the panel. Another example is the company Future Factories, which allows clients to design lighting features, jewelry, and other items that can be directly ordered online. And there are companies offering commercial evolutionary design tools such as Genometry's Genovate technology that integrates with CAD softwares, computer-assisted design softwares. Other evolutionary consumer design systems include Ecosystem's Unch engine and Affinova's IDEA technologies. Although evolutionary design can theoretically access a very large search space, it has been observed that evolutionary design systems often have a recognizable style. As Matthew Lewis says, the signature or style of the outcome that a given evolutionary design system produces often seems stronger than the differences that might result from different users. Typically, the style that a given system tends to produce is the result of the biases that results from the representation and operators chosen. There is a balance to be struck between two options. One option is to give the user an unconstrained design space where the average fitness will possibly be quite low, meaning that a lot of not so interesting material will need to be looked at in exchange for a few surprises. The other option is an over-constrained space that might have too much predefined structure. In systems designed to generate artwork by a single artist, these stylistic biases might be quite welcome. But if the system is meant to serve many users and to cover a large space of possibilities in a neutral way, then stylistic biases are a problem. Without losing focus here, that reminds us of the fact that writing code is writing. We know that even if they are given the same algorithm to implement, not two programmers will come up with the same exact program. The number of parameters and details to be coded in an actual fully functional system makes it a unique one each and every time. Given that design spaces can be made arbitrarily big in most cases, the problem is not whether the Mona Lisa is in the search space. The problem is how to give interesting parts of the search space higher fitness, and in computer-assisted design, how to make high fitness areas as frequent or as large as possible. Ecker and colleagues suggest that we could allow the user to control the biases in large solution spaces to develop a solution space that suits their preferences. Allowing the user to sculpt the fitness landscape is akin to a meta-search to keep from being trapped in a space that does not fit the user's taste or preferences. One of the main challenges with interactive genetic evolution is that the user does not have enough control over the outcome. In many implementations, mating operations often result in offspring that resemble just one or even sometimes neither of the parents. Mutation operations can also be very difficult to control, in the sense of giving the user a way to accurately specify whether they want big or small changes to occur. While automated fitness functions can tolerate large numbers of offsprings with poor fitness, the low population size of interactive system requires design spaces with higher average fitness, and this is hard to ensure. One of the key criteria about interactive genetic evolution systems is how time is managed. Not all systems are equal in this respect. The time needed to review individuals is most often the bottleneck of the system. Reviewing grids of two-dimensional pictures might be faster than reviewing three-dimensional renderings, which is faster than reviewing time-based media like music, animation, video, virtual agents, and other interactive entities, as well as ecosystemic simulations. Depending on the type of system, the computation of the next generation can take a lot of time. This is even more true if several generations have to be computed, as it is often the case to generate a better diversity with high enough fitness. research has been conducted to study and contravene user fatigue in interactive genetic evolution systems. Since evolution consists in a parallel search, interactive genetic algorithms give the opportunity to explore several regions of the search space in parallel. In principle, it is possible to accelerate or slow down the evolution or to zoom in or out on a particular design space and its neighborhood. Sometimes it is possible to manually refine a genome through so-called genetic engineering interfaces, as we saw with the electric chip system. However, in most representations, genes interact with each other when the phenotype is expressed, a phenomenon known as epistasis in biology. This makes it difficult to predict the actual change that a single gene will cause. This effect will be more or less marked depending on the type of generative program represented and used to construct the search space, L system, mathematical expression, grammar, etc. Interactive genetic algorithms involve human computation or hybrid computation, where some part of the computation is performed by human users and the rest by the system. Some systems tap into the potential of collaborative or group creativity by integrating crowdsourcing mechanisms, like the endless form systems we saw together. However, we still need better methods to combine human and machine creativity in ways that harness the strengths of both. While interfaces are usually designed with the principle that simply selecting preferred individuals will gradually evolve improved individuals, the truth is that the user experience and knowledge of the system often plays a bigger part than their objective curatorial role as meta-designers. Since finishing the last detail of a design is best done using traditional tools, it is important that the tools interface easily with other software packages and tools. Finally, distributed design happens in parallel, but it allows cumulative progress when users can build on the results of others. In conclusion, with online deployment and persistent systems that allow multi-user input and branching, computer-assisted design tools powered by interactive evolutionary computation are allowing for radically new design processes. But the interactive evolutionary examples we have looked at are just a small sample of what evolutionary computation has to offer to design and architecture. Another important area of evolutionary design is using automatic fitness functions for design and architecture. In defining the fitness function of a particular design or architecture, one can simply directly apply Louis Sullivan's principle, form follows function. This is akin to simply reducing the fitness function to the utilitarian dimensions of design and letting the evolutionary process shape the individual's forms accordingly. Let's look at an example of completely automatic design. Let's say we want to design a bridge or a scaffold from a given origin to a target point using Lego blocks. A possible objective measure that can be used as fitness function is the normalized distance between the place where the structure reaches so far and the target. Looking at this equation, that is the normalized distance between S and T, where S is the structure and T is the target point. The normalized distance is 1 minus the ratio between the distance between the structure and the target versus the distance between the origin and the target. The researchers Pablo Funes and Jordan Pollack applied genetic programming to this problem through their evolutionary design system EvoDAC in 2000 that evolves Lego constructions. In this particular case, the target fitness was reached after 133,000 generations. Here is another example with a scaffold evolved in 44,000 generations. Through these examples, we can see the drawbacks of the form follows function approach to genetic programming, because it seems that there is no real design or architecture principles applied to that bridge. There is no clear notion of readability, that is, of a design that makes sense according to human perceptual standards. And consequently, there is no notion of aesthetics. So this way of looking at the design problem is similar to the usual optimization performed in other industrial domains. The fitness function measures performance and aesthetic considerations are simply ignored. Another example is the NASA antenna that we studied earlier. They definitely do not look particularly pleasing, but it doesn't really matter in that particular case. But some authors have added aesthetic criteria to otherwise utilitarian fitness functions. For example, Gregory Hornby and Jordan Pollack have used evolutionary computation to evolve tables that maximize height, usable surface, and stability while minimizing the amount of material required. Here is the example of a champagne bar that was actually built in 2003. In evolutionary architecture, the importance of multi-objective fitness functions becomes very clear. John Frather, author of the seminal 1995 book An Evolutionary Architecture, has done research on procedures for controlling growth and development from seed forms into emerging structures rooted in biological strategies, using many techniques from generative art and artificial life research and balancing these with aesthetic principles. The Italian architect Celestino Sodu has also been one of the most vocal advocates of evolutionary architecture and design. He is also the organizer of a yearly conference on generative art. Here are some architectural renderings developed using evolutionary computation for various calls for projects in Hong Kong and the US. An approach that goes beyond computer-assisted architecture or design tools is that of Marcos Novak. The ideas he developed through his work on liquid architectures and related systems consider a different type of architecture that embraces the possibilities of the digital using virtual worlds and evolutionary computing. In Cyberspace First Steps, he says, liquid architecture is an architecture that breathes, pulls, leaps as one form and lands as another. Liquid architecture is an architecture whose form is contingent on the interests of the beholder. It is an architecture that opens to welcome me and closes to defend me. It is an architecture without doors and always, where the next room is always where I need it to be and what I need it to be. In other words, architecture is not made of objects anymore, but made of agents. These ideas of transforming buildings and objects into agents are still very popular in urbanism, architecture, and design, with trends such as smart cities and the Internet of Things. Here is an example of a composition created using a genetic algorithm. This image is then used for further investigation of how information can be specialized. This is a three-dimensional algorithmic composition that maps the previous image onto the environment of a cyberspace chamber. The power of genetic programming also resides in its potential for abstraction. One can search a space of spaces by not simply encoding the forms, but grammatical rules or L systems of shape grammars, which we studied earlier. Several interesting surface-generating systems using techniques such as L systems and agents have been proposed by the Emergent Design Group at MIT, including GenR8 and Agency GP. Paul Coates has used L systems and shape grammars to breed structures using fitness functions based on performance. The fitness function measured the structure's response to environmental conditions such as light and wind, or structural properties like enclosure and permeability. In conclusion, the idea of applying evolutionary computation to a generative technique itself is a way to raise the level of abstraction and the generality of the search. Each instance of the generative technique at hand defines a space, and the evolutionary computation navigates the space of spaces. The evolutionary computation framework will evolve the right setting for the generative techniques to generate what is considered fit. This is meta-creativity, in that we are breeding generative or creative systems themselves. This extends the idea of exploratory creativity toward that of transformational creativity.